All right. So topic 3, we are going to study about fluids. What do you understand by fluids? Anyone can shed some ideas about what do you understand about fluids? Is it a solid? Yes or no? Do not fixed shape, liquid or gas, very good. Okay, so fluid is something that can flow as long as if you place it at a spot. Yes, if you place it at a spot and it will not have a fixed shape and it will flow, then that is fluid. So the example of fluid can be air, liquid, or paste. The paste is just like the dough that you make when you want to bake cake, right? When you mix all the flour together and you get something like paste-like things. So this is also fluids. As long as if it can flow, then that is fluids. All right. So the learning outcomes. So in this topic, we will study about the property of fluids, and some of them you have already studied it in your semester 061. So for fluids, instead of mass, usually we will call them in terms of density. Okay, we will measure in terms of density. Okay. And another one is about the pressure. So instead of we mentioned about force, when something is dealing with, when we are dealing with fluids, we call it as pressure. For example, when you go down into the water, like when you go diving, you won't say, the force underneath the water is very big. You will usually say, oh, I feel the pressure of the water is quite huge when I go deep down into the water. All right. So there are three principles related with fluids. The first one is Pascal principle. The second one, Archimedes principle. And the third one, Bernoulli principle. So these first two principles, Pascal and Archimedes, are related with static fluids. Static means it is not moving. So is the fluid which is not moving. It's just about the property of the fluids. Yeah. However, for Bernoulli equation or Bernoulli principle is related with dynamic fluids. Dynamic means it is moving. Okay, so it's moving fluids. The property of fluids when it is moving. Okay, so density of definition of fluids means substances that flow, and it will take the shape of the container. So the parameters that we use to measure fluids are density and pressure. So density given by symbol rho, calculated by dividing your mass with volume. M stands for mass in the unit of kg. V stands for volume. So this is a big capital V, stands for volume. We have another V, which is small capital V, that is for velocity. So volume, big capital V in the unit of meter cube. So from our calculation, we can predict the SI unit for density is in kg per meter cube. All right. The second parameters, which is pressure, given by symbol capital letter P, calculated by dividing force with area. So F stands for force. in the unit of Newton. Air is area. So this area refers to area of contact. For example, if you are wearing a flat shoes and stamp it and in contact with the floor, right? So this is your area. The contact area, this is your area. However, if you are wearing high heel, for some ladies, so if you are wearing high heels, then your contact area will be here a bit, here and here only. It won't be the whole surface anymore, but only the part that when you are in contact. So that's why pressure is directly proportional with the force. Force here. Remember in our free body diagrams, our weight is also one kind of force. So if you are heavier, then the pressure that apply on the floor will be higher. At the same time, pressure is inversely proportional with the area of contact. So if you are wearing high heels shoes, which means your area of contact is now smaller, then the pressure that apply is also higher. Okay, so if next time when boys, if you laugh at girl, hey, you are so heavy, the pressure that you apply is so high, you say no, because of it's not because that I'm heavy, but because of the contact area is smaller. Okay, so the pressure from our calculation predict your SI unit for pressure. So Newton per meter square, or Newton per meter square also equals to Pascal. Okay, so this is the SI unit for pressure. Okay, remember Pascal, because in your questions, usually they will give in atmospheric, yeah? Okay. So pressure can also be found with this. So this P equals to rho GH is gauge pressure. What does gauge pressure means? Gauge pressure means it is the pressure that relative to atmospheric pressure. Okay, so it means that we will take our atmospheric pressure as the standard, okay, as 0. So whatever top up pressure that you receive, that is called as gauge pressure. So for example, if you are diving down into the water, all right, so the total pressure, or we call the absolute pressure, I mean the real pressure that you receive here down inside the water, is actually equals to the atmospheric pressure plus the pressure that applied by the water on you, correct? All right, so that is what we call as absolute pressure, or we say the actual pressure. However, the gauge pressure is relative to the atmospheric pressure, so which means it's only equals to the pressure that applied by the water. Only equals to pressure that applied by the water, because you have to minus the atmospheric pressure. So in short, we can say that so there are two types of pressure. So in short, we can say that, okay, one is absolute pressure, just a recall from what you have learned before. P, so subscript ABS, ABS stands for absolute. So this is actual pressure. Which is inclusive of atmospheric pressure. So if I ask you what is the absolute pressure that you are experiencing now, it is 1.01 times 10 to the power of 5 Pascal, which is equal to atmospheric pressure, right? So everyone should experience this pressure, unless you are now down underneath inside the water. Okay. So the second pressure, which is the gauge pressure. So given by P subscript G, this is the pressure difference. Relative to atmospheric pressure. And you can find this gauge pressure with rho GH. Okay, H is the depth in the unit of meter. Okay, so applying the same question just now, what is the gauge pressure that you feel now? The answer should be 0. Because if you minus the atmospheric pressure, gauge pressure is okay. Usually we will write down atmospheric pressure equals to, absolute pressure equals to atmospheric pressure plus your gauge pressure, right? So if the absolute pressure that you are experiencing just now was 1.01 times 10 to the power of 5 equals to atmospheric pressure times plus your gauge pressure. So the gauge pressure that you are experiencing now is equals to 0. All right. So that is the difference between these two pressure. Absolute pressure means the actual pressure, inclusive of atmospheric pressure. Gauge pressure is the relative pressure. Okay? So once we have some knowledge about pressure, so let's see the relationship between the pressure and the depth of the object down underneath the water. Okay? So we will use water as the example in this topic because the pressure that we can feel in the water is larger as compared to the air. Okay, air is also a fluid, so there will be pressure difference with different heights, but it will be really a huge difference before you can feel the pressure difference. When you go up, when you go to the very tall place, then only you can feel much difference. So for this one, we will use water. Okay. So when you submerge something down into the water, okay, you will feel different pressure. Okay. So the deeper that you go, the higher is the pressure, right? If you went diving before, one is when you are near to the surface, you won't feel much pressure. Okay, but if you go deep down into the bottom of the sea, you start to feel the pressure, especially your eardrum. Okay, so we will say the pressure P2 here and P1. P2 is larger than P1. So if P2 is larger than P1, so definitely pressure will move from higher to lower pressure, right? So you can imagine that there will be a force trying to acting upwards. Okay, so this force that acting upwards is something that I would like you to pop out into your free body diagrams dictionary. So this is what we call as buoyant force given by F subscript B. Okay, so this buoyant force only exists when object is submerged in fluids. Okay, so in our real life, when we are inside the air, actually there is also buoyant force, but it's very, 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 very insignificant that we have to ignore them. Okay, but when you go inside the water, that is different, because the buoyant force inside the water, due to the density of the water, so it is significant. So that's why unless you are comparing, unless your situation is very, very tall, otherwise in our real life or in our question here, usually we won't consider buoyant force when we are on the ground. Yeah, okay, because it's too insignificant. But when inside the water, we will consider them. All right, so this buoyant force is an upward force. Direction is an upward force. Apply on an object when the object is submerged in fluids. So remember, when you have an object, if you throw them inside the water, when it is dealing with fluids, immediately you draw an upward force for the buoyant force. And since the object has a mass, so you must include also weight. So these are the two types of forces that involve with an object submerged in fluids, or we say submerged in water. So this is also explained by Archimedes' principle. Archimedes' principle says that the buoyant force of the object is equal to what the weight of the fluid displays. It's not the weight of the object, it's not the mass of the object, but it's the weight of the fluid. Weight is equal to W, right? W equals to mg. So this weight is the weight of the fluid displaced. Okay, so it is equals to weight of the liquid. So if you expand weight of the liquid equals to mg, g is gravity acceleration, 9.8 meter per second square. So m here will be the mass of the liquid, right? So this mass of the liquid is not the whole liquid, but it's only equals to the liquid that displaced by the object only. So from our density, density equals to m mass over volume. So mass equals to density times volume. So replace rho v into m, you get rho vg. So density, this will be the density of the liquid. V volume will only be the volume that displays only. So this is how we find the buoyant force of an object. So let's say if now we throw this object into the water. So the volume that you have to calculate here is the volume of this object. Because why? Because now the object is being submerged completely down into the water. So this is the volume. All right. If you have another object submerged partially in the water, so now your volume will only be this part only, because this is the part that displays the amount of water. Okay. according to Archimedes' principle, the buoyant force of an object equals to the weight of the liquid it displaces. True or false? True or false? True, huh? So equals to the weight of the liquid that displaced. So weight of liquid displaced equals to mg. So m stands for liquid displaced. So from density, m also equals to rho v. So density of liquid, v is the volume displaced, g. Okay. So how do we know whether the object will sink or float? So from our free body diagram, yeah, how do we know whether the object is moving or stand still? It depends on the net force, right? If your net force of the free body diagram is going upwards, then the object will float. So to have the net force going upwards, which means your maximum buoyant force should be larger than the weight of your object. When I say maximum buoyant force, yeah, mg, yes. When I say maximum buoyant force, it means when the object is submerged fully down into the water. Okay, it means when the object is submerged fully in the water. So it means that the maximum buoyant force, when it is larger than the weight of the object, the net force will actually act upwards, so causing the object to float. Likewise, if your net force is going downward, then this object will sink. So in this case, which means that the maximum buoyant force of the object is now smaller than the weight of the object. So the net force will go downwards, then the object will just sink down to the bottom. All right. So when they are in equilibrium, which means when the object is not moving anymore, that is when the certain point of the buoyant force is just equals to mg. So in this case, when the object stops moving, right, and it stays still here. So this is when your buoyant force at this point is equals to mg. So at this point, your buoyant force, your rho vg, so v will be this amount of volume only. Okay, so just treat it as a free body diagrams questions, and you solve them according to what type of question that is asking, then you solve the equation. All right. So from there, we can also find the fraction of the object that's submerged down into the water. So it is actually based on the density of the object. Okay, so this is like how we usually, before we learned about buoyant force, we have already known that it is because of the density. Okay, so the lower the density, the lighter is the object, right? If just like your oil and water. So when people ask you, hey, why does oil is on top of the water? Usually you will just answer, oh, because oil has lower density. Okay, so from our buoyant force, if we cancel off this G, yeah, because they are both same property. So when you rearrange, okay, we can calculate the ratio. between them. So from there, we can actually calculate that how much is the volume that is displaced by this object. And this amount of volume that displaced by this object is actually equivalent to how much the object will be submerged down into the water. Okay. So let's look at one example on how do we do the calculation. 70 kg. So this object is with a mass of 70 kg. Lies at the bottom of the sea. So meaning that this one is sinking. So when sinking means your total mg is larger than your maximum buoyant force. Volume, total volume of the object is 3 times 10 to the power of 4. So how much force is needed to lift it? At the density of the water as 1020. So draw your free body diagrams. When something is down into the water, it is related with fluids. So we have an upward force, which is called as buoyant force. So this object with mass, so we have mg, which is going downwards. So from our free body diagrams, upward force equals to downward force. So buoyant force equals to mg. Buoyant force, okay. So from the questions, you need an external force in order to lift this object upwards. So this is external force, or we say the applied force. So upward force have to include the applied force as well. Okay, so applied force plus buoyant force equals to rho Vg, right? Rho, density of the liquid. Now it's inside the sea. Volume, the object is submerged fully down into the water. So volume displaced will be equals to volume of the object times G equals to mass. Mass is the object itself. Mass of the object times G. So plug in the values. Density 1020 times the volume of the object, which is this. 3 times 10 to the power of 4 times 9.8. Mass of the object 70 times 9.8. So the buoyant force 386, or you round off into two significance figure, 390. Okay, so this is the external force that you need to apply on this statue. Oh, okay, sorry. Yeah, it's centimeter cube, so I have to do unit conversion. Thank you. So how to do unit conversion? Convert to meter cube, yeah? So 1 meter equals to 100 centimeter. So cube to the power of 3 times 9.8 equals to 70 times 9.8. Yeah. So this is how you will get 390. So you need 390 in order to lift up this object. All right. Let's look at another one. A super tanker has a total mass. This is the mass of your object. So imagine the dimension of the ship. It's in rectangular box. So this is the dimension. Determine how far the bottom of ship is below sea level. Okay. So this is when the super tanker is in the equilibrium. Okay, it is now not moving, floating somewhere on the water. So this is now in equilibrium. So from our free body diagrams with a mass, so there is a downward force, which is a weight. And since this is dealing with water or fluids, so an upward force, the buoyant force. So free body diagram, upward force equals to downward force. We have buoyant force equals to mg. Expand your equation, rho vg, so that will be density of C. V is the volume that displays, which is here only. G equals to mass of the object times G. Density of the C. Okay, V displays is unknown yet. Mg 1.10 times 10 to the power of 9 times G. So cancel off the G. Volume displaced is equals to 1.08 times 10 to the power of 6 meter cube. So how do we find the volume? Imagine the supertanker as rectangular box. So this is your supertanker. So this, perhaps, this is the amount of water here, right? So we want to find what is this volume. Okay. So we know that the length 220, wide 74 meter. The total height is 74, but what is this h? Okay, so we want to find this. So since the total volume is given by 1.08 times 10 to the power of 6, can we find the height? Yes, yeah. So 220 times 74 times height equals to 1.08 times 10 to the power of 6. So the h values 66.3 meter. Okay. Any questions about Archimedes principle? If no, then we move on to Pascal. Okay, so Pascal, you also have learned it in your high school. What does Pascal say? So it says that a change in the pressure applied to an enclosed fluid must be enclosed fluids, and these fluids must be incompressible fluids. What is incompressible fluids? It means you cannot squeeze it anymore. All right. So when the fluid is incompressible, in chemical terms, it means that the atom arrangement, they are quite concentrated together. Okay, just like solid, you cannot press it to change the shape, right? Okay, so for certain fluids, when the atom arrangement is quite close together, you also cannot compress it. You can change the shape, but you cannot press in order to squeeze it. Okay, so it is only applicable to incompressible fluid. So in this case, it will be like liquid or paste. Gas, somehow you can compress, right? Because why? Because the molecule in the gas is quite far away. So when you compress, you can still release some space inside. All right. So Pascal principle is only applicable to incompressible fluids, and the condition they must be in enclosed container. Okay, so any change of pressure that apply in an enclosed incompressible fluid is transmitted to every portion of the fluid and to the walls of the containing vessel. what does it mean? It means, let's say, if I apply a force here, downwards here, so force divided by this area will be equals to, let's say, your P1. So if I apply P1 here, this P1 will be transmitted equally to every portion of this container. So every part here, the blue color arrow will receive the same amount of P1. So that's why this principle has been applied in your toothpaste. Okay, the paste is being contained in an enclosed container like this. So any point when you press on the toothpaste with your cap open, how much force that you apply, then how much paste will be released out from the toothpaste or from the container. Why? Regardless where you press, you will still get the same amount of the paste, okay, because of this Pascal principle. All right. So in your high school, you only learn about the principle or the definition. So now when it comes to foundation, top up a bit with calculation. So since when you apply P1, it is same as P1 at other points. So we will say that at point 2 here, the amount of pressure that you receive is also equals to P1, right? Okay, or we put another name here as P2. So we will say that P1 is equals to P2. Okay, so what is the formula for P is F over A. So P1 equals to F1 over A1, P2 equals to F2 over A2. Then this is how we do our calculation, yeah? Okay, this is the amount of force at point 1 divided by the area at point 1 equals to the amount of force that released at point 2 divided by the area at point 2. Okay, so this application is also lead the scientists to invent the hydraulic pump. Okay, which is very helpful, especially in car repairing. Okay, so any question? If no, then let's take a break for 5 minutes. And we shall come back at 8:45, all right, to continue with dynamic fluids. 8:45. Move on to the dynamic fluids. So when fluids is flowing, there are two types of flow. One is laminar flow and one is turbulence flow. Laminar means it is gentle river flowing. So by the word itself, you can actually expect that the flow is somehow in a straight line. Okay. So the flow is gentle. So if you have ever visited our lab before, there is a laminar flow cabinet whereby this cabinet is used in order to conduct some microbiology experiments, because we know that the germs, they are very, very tiny, very, very small, right? So it is too small, or imagine as spores. It is too small when there is a flow. It can bring the spore to move together with it. So we need the laminar flow so that there won't be any cross-contamination. Because imagine if you have turbulence flow, okay, turbulence flow, you will imagine the flow is not straight line like this, but it will be up and down, okay, rolling or very erratic. So if the flow is very erratic, then you will have the possibilities to get cross-contamination. Let's say if you have 2 plates of microbes, okay? If the flow is laminar, then it will flow bypass all the plates, right? But if the flow is erratic, like this, then perhaps from this plate, the virus will be brought from here and touch your another plate. So that will be cross-contamination. All right, so this is why sometimes we have to look at the flow also, the fluids, the flow of the fluids. So when it comes to engineering, this is the things that you are going to study. So let's say if I would like to conduct this kind of experiment, yeah, then what kind of flow? Then this is what you have to consider also. All right. So no matter what type of flow it is, the total amount of the fluids will remain the same. So it means that the total volume flow rate of the fluids will remain the same. So total volume flow rate is, okay, this is volume, yeah? Big capital V is volume. So volume flow rate is volume per time. This is time. Unit meter cube, time is in seconds, yeah? So the total volume flow rate will be the same. Okay, so for example, inside this container, regardless how the flow it is, whether it is laminar or turbulent, the amount of the volume flow rate at this point and at this point will be the same, okay? Because that is about the the volume. However, what will change? Your velocity might change. Okay, the velocity, small capital V, might change. All right. So the volume flow rate in degree, in my degree last time we give this as Q. Okay. So in your degree depends on which engineering you are taking. So you might usually there are 2 engineerings which will use much of the fluids knowledge, which is mechanical and chemical. Civil also. All right, so these 3 engineerings you will need this knowledge. So the volumetric flow rate, the volume flow rate will be the same. All right, but what will change is your velocity. Velocity will be different, but the total volume will be the same. Yeah. So from here, if we say Q equals to change of volume divided by time, okay, this is capital B. Volume is equals to cross-sectional area times the area, right, times the distance traveled, right, equals to time, divided by time. So distance over time also equals to velocity. So area times velocity. All right. So volume flow rate equals to volume divided by time is also equals to cross-sectional areas times velocity. So since Q1 is equals to Q2, we can conclude that A1 V1 is also equals to A2 V2. Remember now this small capital V is your velocity in meter per seconds. Okay, so this is what we call as the equation of continuity. And this one is only applicable to dynamic fluids, yeah? Okay, so this is an example of the laminar and turbulent flow. So if you would like to see whether the flow is laminar or turbulent, you can use dye. Okay, dye is very light, so it will move together with the fluids. So you can see the movement of the dye in order to determine whether the flow is turbulence or laminar. All right. So another principle that related with moving fluids is Bernoulli principle. So this Bernoulli principle is very powerful. Okay. It is also being used now in the industry. Okay. It's all based on Bernoulli principle. Okay. It is also applying to conservation of energy. So it actually takes account into the pressure of the fluids. This is absolute pressure of the fluids at the point, the velocity of the fluids, and also the elevation, the position of the fluids. Because the fluids, when they are at different altitude, there is different pressure. So it will actually affect the pressure of the fluids. Yeah. So the derivation of the Bernoulli equation is something extra. You can find it on Moodle. I label it under item 0. So that is for your information only. Otherwise, okay, you can just memorize this equation, yeah? Because it will be used quite frequently in degree. So I think you can consider memorizing it. So it says that when the fluids move through a region where its speed, okay, there is a change in speed, or there is a change in the position, or we say change in the height, above or below the earth, yeah, above the earth, or above or below the sea level, right? The pressure in the fluids will vary with this change. Okay, so P here, big capital P, stands for the absolute pressure. Remember the SI unit for pressure is in Pascal or Newton per meter square, plus half rho V square. Rho, density in kg per meter cube. V, this is a small capital V, so it is velocity. Velocity of the fluid in meter per second, plus rho gy. Rho is the density, g is the gravity acceleration, and finally y is the elevation. Elevation means the height. So usually for this one, you need to have a reference point which is as 0, and how much is the elevation? Okay, so the total equation, the total expression here will be the same for every point. That is conservation of energy. All right, so the first one, this is the pressure of the fluids, the absolute pressure of the fluids. And the second one, half rho V square. This one is related with the kinetic energy of the fluids. And the final one, rho Gy, is related with the elevated potential energy of the fluids. Okay, so these are the two factors that will affect your pressure of the whole fluids. All right, so if the fluids, they are the same, then the total expression here at point 1 is equals to the total expression here at point 2. Okay, so this is what we will do with our calculation, yeah? Do you need times to memorize them? If you cannot memorize, it's okay. It will be given in the formula sheet as well. But if you want to pursue chemical, mechanical, or civil engineering next time, then I will encourage you to start memorizing it now, okay? Because you will be using it quite a lot, yeah, in your degree. It doesn't say that if you want to go for electrical, then you don't need to memorize. There is always no harm to learn more, right? Since you have a powerful brain, why not we go and memorize powerful things? Okay, so now please state the Bernoulli equation. So P1 plus kinetic energy rho V1 square plus potential rho Gy1. So is equals to constant. So you can write down, or you can write down in terms of P2, V2 plus Y2. Huh? So that is Bernoulli principle. So how do we apply it in our calculation? So usually for Bernoulli principle, at our level, we will assume the viscosity is negligible, okay? So viscosity is also one of the factor which will be top up in your degree letter. Okay, so we won't load you with too much things first, but first get used with the utilization of this Bernoulli equation. Density of water given by 1000 atmosphere, and it is at atmospheric pressure. So this is atmospheric pressure. So water flows at the speed of 4.4. This is velocity. So let's assume as V1. Diameter, when it is at 3.5 centimeter, your velocity is 4.4. So let's assume 3.5 as D1. Gauge pressure P1 of the water in the pipe. So this is gauge pressure. Bernoulli principle. Okay, Bernoulli principle is what you have learned in high school, right? It says that when the velocity of the fluids is higher, the pressure of the fluids is lower. When the velocity is lower, the pressure is higher. Okay, if the definition it is not included here, because we will move we move on to the equation straight away. Huh? Okay. If you would like to know the definition, yes, it's something that you have learned in your high school. It's related with the velocity. Yeah? That is Bernoulli Bernoulli principle. Okay, but now what we are looking here is the equation. How are we going to apply the equation? Huh? All right. So this is gauge pressure 1.2 atmospheric gauge pressure at 0.1. So we put it as PG1. So a short segment of the pipe is constricted to a smaller diameter. So this is diameter. So D2, 2.2 centimeter. What is the speed? Find V2. Okay, so usually for Bernoulli equation, you can write down all the information that you extracted, okay, from 0.1 to 0.2. Given atmospheric pressure, 1.01 times 10 to the power of 5 Pascal. The gauge pressure is 1.2 atm. Convert to SI unit, 1.2 times 1.01 times 10 to the power of 5, 1.21 times 10 to the power of 5 Pascal. Diameter 1, 3.5 centimeter. Velocity 1, 4.4 meter per second. So what is the absolute pressure at 0.1 is given by atmospheric pressure plus gauge pressure. So atmospheric pressure plus gauge pressure. We have atmospheric pressure, we have gauge pressure. Okay, now let's look at 0.2. P2 is unknown. V2 is also unknown. What do we have? We have D2, which is 2.2 centimeter. And based on our equation, our diagram, 0.1 and 0.2, we can assume that they are at the same elevation, huh? Because the height difference is not much. Huh? So we assume both of them at the same elevation. Now, the question wants us to find what is V2. Okay, so velocity here is caused by the change in velocity here is caused by the change in the diameter. So we can use equation of continuity, right? What does it say? A1 V1 equals to A2 V2. So A1 pi r squared. So 3.5 is in centimeter, divide by 2 to make it meter. Convert to SI unit times 10 to the power of -2 squared, pi r squared, times V1, which is 4.4, A2 pi r squared, 2.2 centimeter, convert to SI unit, divide by 2, make it radian, and solid radius, times your V2. So V2 here is 11 meter per second. Yeah, so when the diameter is smaller, velocity increases. All right, because the area is now smaller, so they have to move faster. Or the fluid is being pushed to move faster. Okay, now question B. What is the difference in pressure between the two ends? So what is the difference in pressure? P2 minus P1. Okay, so now let's find P2 and see what is the change in P2. So in order for us to find P2, we need Bernoulli equation. P1 okay, P1 equals to P atmospheric plus gauge pressure 1, so 1.01 times 10 to the power of 5 plus gauge pressure density V1 4.4. So since Y1 equals to Y2, these two can be cancelled off because when you move them to the other side, it is equals to 0. Equals to P2 is our unknown. V2, 11. So the values of P2, absolute pressure at point 2 is 1.7 times 10 to the power of 5 Pascal. As compared to your P1, the pressure is higher or lower? Just now our P1 1.01. Yes, huh? It is nowhere. It is no, like it is lower. P1, when you plus these two together, you get 2.2 times 10 to the power of 5 Pascal. So compare P1 and P2. P1 in fact is higher than P2. P2 is lower. So remember just now our V2 is higher than V1, right? So this is in line with your Bernoulli principle. When your velocity is higher, your pressure is lower. Okay. So P2 is lower, right? So now our question is, they want you to find what is the difference in between these 2 points. So change in pressure. Wait. What is your question? Why would Y be if there is a value? Oh, if the question gives you, so in this case, the question does not give you, yeah? So usually if, let's say if the Y has to be considered, the question will give you, let's say they will say, oh, the height difference is perhaps 2 centimeter maybe. 2 centimeter. So usually what we will do is we will assign this one as Y1, and this will be our reference point equals to 0. Then that will be our Y2 equals to 2 centimeter. If that is the case. So for this case, the question is nice to you because it does not give you any information about Y. So based on the picture itself, usually for Bernoulli principle, there will be a lot of assumption. Okay, there will be a lot of assumption which you have to make. So if, let's see here, if the distance is too small, usually we will just assume that they are equals to the same because the difference is not significant in order to make any changes on the pressure as compared to, let's say now, because of the velocity. Okay, so in this case, if we look at the velocity, the difference is quite huge, right? So the change of the pressure that caused by this velocity is now much significant as compared to the elevation. Okay. Because P1 is absolute pressure, for Bernoulli equation, remember your P pressure here must be absolute pressure. Must be absolute pressure. If you put in gauge pressure, then your whole equation is wrong. All right. So it must be absolute pressure. Okay. So what is the formula for absolute pressure in our earlier explanation? Or from what you have learned in your previous semester, absolute pressure equals to gauge pressure plus atmospheric pressure, because that is the actual pressure that you are experiencing now. Okay, what is the next question? Yeah. Of both side normal. You can assume that, or even though is absolute pressure is constant, not really your absolute pressure is constant. Not really, depends on your gauge pressure. Atmospheric pressure is constant, it won't change. No matter where you stand on top of the mountain or you stand at the bottom of the sea, atmospheric pressure will not change. But absolute pressure will change depending on where is your location, huh? The Y point, the point for the Y, you can assume that you take it at the center point. Okay, you can assume it is at this center point. You can assume it is at this center point, so there won't be any change in Y. Yes, that is one of your assumptions. But however, even though if we take these 2 points, the change in Y still considered as equals to 0 because the change in the height is too insignificant. Okay, that is one thing for Bernoulli principle. There have to be a lot of assumption, okay, in order for us to solve some equation. Okay, so for this case, let's say we have already done one assumption. In your syllabus, we have already assumed that the viscosity is negligible. All right, so for in this case here, even though now your point y1 and y2 as in these two locations, the change in the height will be assumed as negligible because the distance is too small. Okay, so again, in your syllabus, it is because our aim is for you to get familiarized with the application of Bernoulli equation. We want you to know how to use this equation. So in your case, I mean, just for your syllabus for now in foundation, if the question does not give you any height, okay, then it means that the change in height is negligible. But if the question gives you, which means you have to include in your calculation. All right. But when it comes to degree later, then you will be slowly top up with certain properties that you have to include in your equation. So for now, just get use of this, the application of the Bernoulli equation first. Okay, but when it comes to degree, there will be also a lot of assumption. So get prepared for the fluids. Huh? All right. So now let's find the change in the pressure. So P2 minus P1 or can be P1 minus P2. Okay, both of them will give you the same values, just that one will be in positive, one will be in negative. But now the positive or negative does not affect your result because we only want to find the difference. So since we know that P1 now is larger than P2, perhaps you can write down P1 minus P2 and we get 0.5 times 10 to the power of 5 Pascal. Okay, so that is our answer. The difference in pressure. Any question about Bernoulli principle? Or Bernoulli equation? Do you need some time to digest? So now let's look at the application. So I guess for Bernoulli principle, you all are quite familiar. Okay, the application about for civil engineer, you need to know the pressure change. So in order to connect the pipe or even the strength of the pipe itself. If let's say the distance is very tall, the change in pressure is very huge. So your property of the pipe has to be very strong in order to withstand the pressure. So this is why civil engineer also needs to learn about fluids and aeroplane. So if you are a mechanical engineer or an aerospace engineer, so this is I think this is the greatest application of Bernoulli principle for the invention of the aeroplane itself. The wing, okay, why is it moving like this? So on top of the wing, due to the shape of this aerofield, okay, it causes the velocity to be higher on top as compared to the bottom. So it helps the flights to lift up into the air, okay? And during landing or takeoff, you will see a change in the directions of the wing in order for the flight to take off easily and landed safely. And also the spoiler of the car. So for those who would like to race car, usually they will have a spoiler behind. Why? Because of the shape itself, it will cause the car to be more stable. Okay, there is a downward force causing the car to go down, to stick down to the road. Otherwise, or when you are driving too fast, remember, higher velocity will cause lower pressure. So if you are driving too fast, your car might be drifted away, which is very dangerous. So you need that spoiler. But I don't wish my students to be a racer. And also the nozzle. Okay, how do you spray the things out? Okay, so I would like you to take a picture of this question. And if we have, and we shall discuss this during our tutorial section. Just take a picture of this question. Application of Bernoulli principle. And this is by elevation. No? Have you done taking the question? Three. Annotated, won't it be inside? Yeah, it will be lah. It will be inside the annotated slide. Oh, you all don't want to have this question in your phone, huh? Okay, so we have another 10 minutes, so let's have a short Kahoot session. Huh? Just some conceptual question. Okay, go to Kahoot.com, filling the pink. You can think of some creative names for yourself. Can you hear my voice? Is the music of the... Can you hear me? Cannot. Huh? Can you hear my voice now? Can you all hear me just now when I was sharing the... Oh, okay. How about now? Can hear now, right? Okay, not really, huh? Okay, so let's start now. Only 5 questions, no? Oops. What happened? Anyone? The 3 can tell me what happened? Hey. What's wrong with this question? Cause yes, remember, gas is fluid, but remember for Pascal principle is only applicable to incompressible fluids. I think I have emphasized that quite many times. Yeah. Okay. So gas is a compressible fluid. Tricky. So that's why I say you have to alert. So in this case, this gas is a compressible fluid. So even though it is a fluid, but when you transmit the pressure down at piston 1, there won't be anything happen at piston 2. Why? Because it is compressible. Okay, so nothing will happen. Very good to the 3. Yeah, these 3, they are the god in your bag. Yeah, so now move on to the next question. Whoa, hey, you are winning. Imagine you are imagine winning. Yes, you are. Okay, and CCC. Very good. Kena tipu. It's okay. It's better to kena tipu now rather than kena tipu during exam, right? Okay, next. Now, instead of gas, it is using water as fluid. So what will happen on piston B? You read the no, you read the question carefully. Jeff, you are funny. Yeah, fully sealed. This time the engineer fixed the problem. Yeah, very good, huh? So this time the engineer fixed the problem. So there is no leak in the piston. Okay, the water, there is no bubble inside the water. Yeah, so when a small push down at piston A will cause a rise in piston B. Very good, due to the Pascal principle. Right, next. Buoyant force. Buoyant force equals to the weight of the water displaced. Very good, huh? It's not equals to the mass of the water. Remember, this is a force, so it has to be in Newton. So Newton is weight. Mass is not in Newton, mass in kg. So it's not blue color. Weight of the object also no. Okay, weight of the object is downward force. Buoyant force is an upward force. So it's equivalent to the weight of the water displaced. Okay, very good. Uh-oh. CCC took over winning. If the buoyant force is just equals to the weight of the object, yeah. So when the buoyant force is equals to the weight of the object from our free body diagram, it is when no net force is acting on an object. So when we say the object will float, it means there is an and action or direction going upwards. Okay, will float. Okay, it means that later on it will go up. Okay, will sink means there is an downward force or net force going downwards, so it will go down. All right, so no net force acts on the object. Oh, you are all correct. Next. Compare the pressure at point 2 and 3. Point 2 is the red color point. Point 3 is the blue color point. So what will change when the diameter change? Okay, now let's look at the difference between point 2 and 3. From point 2 to point 3, the diameter increases, right? So when diameter increases, what will happen to your velocity? From the equation of continuity, when diameter increases, your area increases, right? So A1 V1 equals to A2 V2. When your area increases, velocity decreases, right? So from Bernoulli principle, when velocity decreases, pressure increases. So which means pressure 3 will be larger than pressure 2. Okay, pressure 3 will be larger than pressure 2. So it's yellow color. All right. Dream. You are. Wow, see, very good, huh? Okay, so thanks for your time today. Okay, so I will, yeah, you have next class, right? So that's all for today. If you have any question, you can just send me an email or WhatsApp me. And I shall see 2E2 later in the afternoon. Bye-bye.